In this tutorial, I'm going to show some of the advanced features in Mason's layout tool. This is an amplifier circuit complete with the bias network and connectors. I've defined true grounds attached to the amplifier and the connectors, and also over here where we terminate this coupling cap, bypass gap. You can define the true ground from the power tool options, and it by default is a G&D ground. I've also defined this 5 volt power tool option. Now this 5 volts, we have relay, the DC 5 volt supply, but we also need to consider it as an RF ground. So I've made it a RF ground, but not a net ground, by using the Mason library's RF ground device. Some of our real-world components do not have one-to-one mappings between the actual terminal pins and the S-parameter ports. This is a Hittite amplifier. The manufacturer provides the S-parameter data, the touchstone data, and it also gives us what the footprint is. So I've created a smart footprint. It's file-based. It includes not just the actual physical shape of the footprint, but also how to connect it up. Where they get connected, and the vectors for how to orient the part relative to other parts. But this is a 4-terminal device, 4-pin device, and we only have a 2-port S-parameter model. So I've introduced this concept of a nodes parameter. And the nodes parameter, it maps the 4 terminals, these 4 numbers, to the 2-port model. So we have terminal 1 is mapped to port 1 of our S-parameter model. Terminal 2 is 0, and that means it's not part of the simulation. Don't map it to a S-parameter port. Terminal 3 is this 3rd number, gets mapped to port 2 of our touchstone file, and terminal 4 is also zeroed out, so it's not part of our simulation. It doesn't get mapped. So here we can take a 4-terminal device and map it to a 2-port S-parameter model. I've gone another step beyond with this connector. The connector, I have a 5-terminal device. I've spoofed on the layout a 2nd terminal that's on the signal terminal, the signal pin, so that I can associate a simulation, a little bit of inductance, some parasitic inductance that's going to be modeled in for this connector. And then with that, I can map this 1st terminal to port 1 of my little primitive file, dynamic file, of this inductance. Terminal 2 gets mapped to port 2, and then the 4 pins that are just the DC grounding for the RF connector, those are zeroed out because they're not actually part of the simulation. Up here, we have a header that provides this DC 5 volts. It's RF grounded with that component. So for this particular part, we don't have to provide any simulation information. There's no file, there's no primitive data that's associated with it. All we have to do is provide the package type. And here I'm using a file-based, XML file-based one, which means that it can automatically place this header. But we don't have to worry about like any sort of node mapping with this. Now, I'm going to show the bias network that we have here. It's actually pretty good, and so even if I remove this ground, I don't expect to see much of a difference. But I'm going to go ahead and I'm going to take this off and rerun Mason, and we should see when it completes running a little bit of a change here. Not much of one, but there's a little bit of a change. So let me rerun Mason, and we should see this jump a little bit. Yeah, so right around here you can see a little bit of a change. Again, because we have such a good bias network, you don't notice it that much, but there's definitely a point of actually putting the RF ground correctly there. So now I'm going to talk about this vSense label that I've added. There's a little label button up here, and the reason I've added this is because I actually have the second sheet defined. The second sheet has some of the digital components that are part of my schematic design. Here I have a little microcontroller that has a vSense net attached to an analog input for it, and then I put in a little power here, again just for demonstration purposes. Now, one of the things to notice is that the reference designators that I have here, they're continuous with the reference designators that we have here. We have C3 and then we jump up to C4. The reason why we have that is when we generated the symbol reference, I click this all sheet. It's a good idea, even if you have one sheet, to get in the habit of clicking this all sheets when you generate the references so you don't end up with any sort of glitches. If I didn't have that clicked, then it's C1. And then if I actually tried to run this, I'd have a collision where Mason would probably just get confused. So it's just a good habit to get into to keep those unique. And then these components, again, are not part of the RF simulation, so I just put in a package, not a actual like file or primitive parameter for this. But here, I just have these dumb footprints. These are footprints that the layout software I use knows what a DIP18 is. It knows what a No402 is, but it's not part of an XML file that includes how these parts get connected in, what the orientation is relative to their neighbors. So this is just going to show up in the layout. We're going to have to place these by hand. But for digital parts, that's pretty much what you want to do. So now I'm going to run Mason again, and we're going to pull up the console so we can watch it run. So solving, and now you can see that it's placed a lot of the components based on the components that are around them. So it goes through and iteratively places all the components that are the smart footprints relative to each other. And then let's go ahead and pull up the layout. Alright, so here we can see our layout. These are the two connectors that we had. There's our little 4-terminal amplifier. We have all of our capacitors that were used here connected up. We have our RF grounds are all associated. Our 5 volts, 5 volt net is associated down to the second sheet where we had this microcontroller. We have the vSense net is linked between where we're trying to sample the voltage and where we're trying to capture the sense of the voltage in the microcontroller. And we can go ahead and rotate some of these, and at this point all you'd have to do is complete your board outline and your ground planes, and the critical RF components would be already laid out. A couple other things to point out. So in general, we map these microstrip lines to somewhere around the center of the where they get de-embedded. The terminals are electrically trying to model the length of the microstrip line, and it's not really accurate to map these de-embedded things like right to the edge of the physical pad. This is especially true when you're dealing with vias. Headers, this header is less important. It's just important to be aware when you're trying to get the headers and connectors and devices a certain length away, that the electrical length and the physical length might differ a little bit. The other thing to be aware of, and this gets a little bit deeper, when you have your cams, if you're using the pads layout tool and not importing this into something else, when you look at your solder mask. Let's go ahead and preview this selection and zoom in. So you notice that it's pretty much left everything here to be exposed. Everywhere that you see the black is where you're going to have exposed copper. So one of the things that you might want to do is consider in your options, we can exclude certain reference designators. So anything that's a TL or a T component, we can suppress that. And so now if I preview my selections, now I have something that's much closer to what I actually want in terms of exposed metal.